Before we start going into all the individual planets in the solar system and all the moons in the solar system and talking about their properties, I want to give a really quick overview of the solar system as a whole. We did a little bit of this very early on in the course when we talked about just the scale of the universe, and we talked about the solar system in that context, but I want to review it again because there's some important vocabulary that needs to be laid out before we talk about the individual planets. When we look at our solar system and just look at the planets, one of the things we notice is that there is a very clear dividing line between what's going on in the part of the solar system that's close to the sun and what's going on way out far from the sun. That if you look at Mercury, Venus, Earth, Mars, you can then draw a line before Jupiter, Saturn, Uranus, and Neptune, and that these planets in close and those planets out far away are very, very different in size. They're very, very different in structure, and there's a vocabulary that we came up with when describing our solar system for distinguishing these types of planets. The planets that are close to the sun we call the terrestrial planets. The planets that are far from the sun we call the Jovian planets. And the differences between them are fairly clear. These are the 4 terrestrial planets in our solar system. Earth, the terrestrial planet that we live on. Terrestrial just means like the Earth. Venus, which is closest to the Earth in size. Mercury, and Mars. These are to scale, as close to scale as I could get them. So Earth is the largest terrestrial planet. Venus, very, very close second. And then Mars, and then Mercury, which is just a little bit bigger than our own moon. The terrestrial planets are all different from one another, but they share some important characteristics. First of all, they are small and rocky, meaning they are made up of metals and silicates, the things that you consider a rock. They are, in our solar system, close to the sun compared to the Jovian planets. They have a thin atmosphere or no atmosphere. Earth, what you think of as an atmosphere is the Earth's atmosphere, right? The Venus's atmosphere is a little bit thicker than the Earth's. Mars is about 100 times thinner. Mercury barely has an atmosphere at all. The composition of the atmospheres of Earth, Venus, and Mars is nitrogen and or carbon dioxide. So lightish gases and molecular gases, CO2 or N2. Oxygen we find in the Earth's atmosphere, but we do not find in the atmosphere of the other terrestrial planets. And the other feature they share is they either have one moon or 2 little moons or no moons, contrasted with the Jovian planets, which typically have a large number of moons. Our Earth has a big moon relative to its size. Venus has no moon. Mercury has no moon. Mars has got 2 little tiny moons that are barely bigger than a small asteroid. So the terrestrial planets in our solar system share these characteristics, and they share the characteristic of being in a similar place in the solar system. Whereas the Jovian planets, the Jupiter-like planets, Jupiter, the prototype Jovian planet, Saturn, Uranus, and Neptune are all far from the sun in our solar system, and they are all much, much bigger than the Earth. There's the Earth as close as I can make it to scale to the Jovian planet. So the Earth would fit between Saturn and its rings. The Earth would fit inside of a minor storm system or a major storm system on Jupiter called the Great Red Spot. The whole planet Earth is the size of one of the atmospheric features on Jupiter. So the Jovian planets are all different from one another, but they also share some characteristics. Namely, they're big and they're mostly gaseous. They have very, very thick atmospheres. In fact, they're mostly atmosphere. We use the word gas giants to refer to Jupiter and Saturn. We used to call Uranus and Neptune gas giants as well, but more recently we've discovered that once you get through the atmosphere, their composition is largely ice. So you'll sometimes hear Uranus and Neptune referred to as ice giants. In our planetary system, the Jovian planets are far from the sun compared to the terrestrial planets, and they have large numbers of moons, anywhere between 12 and 50, 60 or more moons. Saturn has so many moons I stopped counting. Every time we fly a spaceship past Jupiter and Saturn, we discover more moons. And all of the Jovian planets have rings, We associate rings with Saturn because the rings of Saturn are very easily visible. We've known about them since the 1700s. You can see them with an inexpensive backyard telescope. But Jupiter also has rings, and Uranus also has rings, and Neptune also has rings. They are much thinner. They have much less material. They are much harder to see until you get out there with a spaceship and take a picture of them. It's worth noting that until recently, until the past 15 years or so, maybe 20 years, we have not really known about any other planetary systems other than our planetary system, the solar system. So it was a question that we did not know the answer to. Is this arrangement of a solar system typical? Are all planetary systems like this? Little rocky terrestrial planets up close to the sun, great big gaseous Jovian planets far away from the sun. All of our theories of how planetary systems were formed 15 years ago, 20 years ago, were all based on our solar system because it was the only data point we had to tell us what solar systems are like. More recently, we have discovered thousands of planets around hundreds of other stars. We have other examples of other planetary systems. We have examples of planetary systems where there's a Jupiter-sized planet located in its solar system where Mercury is located in our solar system. So gaseous planets aren't always far from their suns. It just happens to be the case in our solar system. So when thinking about planetary systems, we have to keep in mind that our planetary system is only one way to make a planetary system, and other planetary systems may have different characteristics from our own. When you look at the solar system as a whole, you notice something about the orbits of the planets in our solar system. The planets are elliptical, they're oval, but they're ellipses with small eccentricity. They're pretty darn close to circles for most of the planets. And all of the planetary orbits lie in roughly a plane, a flat plane. The orbits of the planets tend to be inclined by no more than 5, 6, 7 degrees from a flat plane. And all the planets in our solar system go around the sun in the same direction. So the solar system is basically a flat plane with everything moving in the same direction and with small tilts and small eccentricities. Everything's moving in a roughly circular orbit, at least the planets. There are things like comets that orbit around the sun in highly tilted orbits, in highly elliptical orbits, very stretched out orbits. But the planets are constrained to this orbital plane. They're constrained to moving in the same direction. We can take this fact about the planets in our solar system. By the way, almost all the moons also go around in that same direction, and almost all the planets spin in that same direction as well. So the direction of the solar system spin is almost all in one direction, with a couple of exceptions of things that were caused by collisions and stuff, which we'll talk about when they come up. This is a hint, this is a clue that tells us something about the history and the formation of our solar system. And this is generally regarded as evidence that all the planets and all their moons and all the comets and asteroids formed at the same time out of the same rotating, collapsing cloud of gas and dust. That the reason everything is spinning in the same direction is because it all formed from the same rotating cloud of gas and dust. We will talk in some detail later about the formations of planetary systems, but suffice it to say that the most simple picture of how the solar system formed is the solar system started as a very big cloud of gas and dust that gravity started to pull in. As it pulled it in, it spun faster and faster and faster, just like an ice skater pulling in her arms. Conservation of angular momentum makes it spin faster and faster and faster. Gravity causes small clumps to clump into bigger clumps and big clumps to clump into huge clumps. And over time, the planets gradually clear out a path through their orbit and grow bigger and bigger and bigger by accumulating material. Most of the mass in the solar system is located in the center. Our sun makes up 99%, more than 99%, I think, of the mass in the solar system. So if you took all the planets and all their moons and all the comets and asteroids and squished them together in a ball, they would weigh less than 1% of the mass of the sun. So most of that material fell into the center and was compressed into what would become the sun. We are the leftover junk from the formation of the solar system. And that leftover junk extends quite a way into space. If you go out to Pluto and beyond, there's a region of the solar system called the Kuiper Belt, which is just kind of leftover debris from this initial cloud of gas and dust that would form the solar system. So that's just an overview of what's in here, what needs to be talked about in our solar system. In the next several videos, we will talk about the planets one at a time. We will talk about the moons of the planets. We will talk about all that leftover junk like comets and asteroids that orbits around our sun in between the planets and beyond the orbit of Neptune.